Hey guys, so this is my solution for Adventure 3 Quest D. I will be solving problem 9.38, where we have an inclined plate at an angle of 45 degrees with net radiation heat flux of 300 watts per meter squared at the bottom surface of this plate. Now, the top surface and the edges are insulated, and so we're asked to estimate the temperature that the plate reaches when the ambient air is quiescent and at a temperature of 0 degrees C. So, in summary, we're given these constants. We're going to make a couple of assumptions to find the surface temperature of the plate. The first one is steady state, the second is constant properties. The third one is that the surface temperature is 50 degrees C, and I'll explain why in a second that I'm making this assumption. 4 is that we've got quiescent air, and then 5, we've perfectly insulated surroundings. So, to start out, we want to determine if convection is occurring at this bottom surface. Now, in order to do that, we calculate the Rayleigh number. Now, the Rayleigh number, we have to make this little adjustment where to add cosine of theta here to account for the angle that it is at. With this equation, we can input most of these things, but we do have to make an assumption here. We have to assume the surface temperature to be some number, and that's also going to affect beta, which has to be in Kelvin, in order to solve this problem. So I've made an assumption here. I will solve the problem with this assumption and then iterate if I need to. Now, when solving this, I get 5.47 times 10 to the 9, which is greater than 1 times 10 to the 9, which means that we have turbulent convection. This means that we can solve the closed system energy balance of our problem here with the convection formula. And we're going to be solving for this surface temperature. Now, in order to do this, I'm going to find H using the Nusselt number as well as the Rayleigh number and the Prandtl number. Any of these numbers, like the Prandtl number or alpha or nu, I found table 8.4 using 300 Kelvin as a rounding estimate, which could change, of course. I found that H is equal to 5.48 watts per meter squared Kelvin, and then I would just plug in H at this 54.72. Now, this is pretty close to our original estimate of 50 degrees C, and we got pretty lucky here. In fact, I need to... we got pretty lucky. But what I decided to do is I decided to create a plot where I solved for these... I solved this equation through this problem, still using all of these constants at 300 Kelvin, but I changed the surface temperature as well as beta here to be ranging from 0 to 100 degrees C. And then I've plotted it against the calculated temperature in Celsius to compare the two. And then in red, I've created this line that is a 1-to-1 slope. This means that when this red line intersects with this blue line, that would mean that our assumed temperature matches our calculated temperature. So this should give us a closer estimate of what the value should be. Of course, there are more variables to vary, but I did not do that. So when I solve it like this, iterating the surface temperature and then solving it, I get that the surface temperature is closer to 59 degrees Celsius. So it's a little bit far off from our initial guess of 50 C, a little far off from what we calculated when we used 50C. But I think that it is a closer answer, a more accurate answer, is around 59 degrees Celsius. And so, yeah, that is my solution for question 9.38. Thank you, guys.